Good morning. And in today's class, we are going to discuss about the conducting materials. You are familiar with this word conducting materials, and you know what is a conductor, right? Generally, we say that that is the material which easily conduct the heat and current is called as conducting material, and otherwise low resistive materials are generally called as conductive materials. And these materials have high electrical and thermal conductivity that you know. So the conducting property of the material that depends on what? It is not a function of the total number of electrons, right? So it is the total number of free electrons or so-called conducting electrons or valence electrons. Okay. So if we talk about the metals, the electrical conductivity that depends upon the total number of free electrons or valence electrons. Okay. So this is about the introduction part. And in order to understand the structural, electrical, cohesive nature, and so many properties, some theories were proposed. And there are three main important theories. The first theory is that is the classical free electron theory. Okay. So this theory was proposed by the scientist Drude and Lawrence in the year 1900. It is a macroscopic theory, and this theory explains how the electrons behave in the lattices and how it obeys the laws of classical mechanics. That is the first theory. So it is a macroscopic theory proposed by the scientist Drude and Lawrence in the year 1900. And this theory explains the free electrons in the lattices and it obeys the laws of classical mechanics, right? And coming to the second theory, that is the quantum free electron theory, because it has some drawbacks and it fails to explain the photoelectric effect, Compton effect, paramagnetism, ferromagnetism, etc. But it has some success also. So that is in this, what are the success of this classical free electron theory means it is used to verify the Ohm's law and to derive the expression for Weidmann-Franz law, that is after getting the electrical and thermal conductivity, it is used to obtain the expression for Weidmann-Franz law. Okay, these are the success and there exist some drawbacks. So in order to overcome those drawbacks, we move to the next theory as the quantum free electron theory. And it is a microscopic theory because previously I told it is a macroscopic theory, and this one quantum free electron theory is a microscopic theory, and it was proposed by the scientist Sommerfeld in the year 1928. And this theory explains the concept that the electrons, how it moves with constant potential. The behavior of electrons, how it moves with constant potential, and this obeys the laws of quantum laws. Okay, so that is the second theory, and it has some drawbacks. Later we move to the last theory as the zone theory or band theory. So this theory, that is the zone theory or band theory, was proposed by the scientist Bloch in the same year 1928. And this theory explained the concept that the electrons that moves in a periodic potential, you know, the previous theory, that is quantum theory, explains how the electron moves with constant potential, and this zone theory explains the behavior of electron, how it moves with the periodic potential. Okay, and based on this theory only, we classify the material as conductors, semiconductors, and insulators. Okay, this is a band theory or zone theory. So you could understand what are the main three theories. And coming to the basic definitions, the first one is drift velocity. Okay, so what the velocity, you know what is drift velocity means? If we apply some external field, because of the field, the electrons are drifted in a particular direction. Okay, so that is nothing but the average velocity acquired by the free electron in a particular direction due to the application of some external field. So this is nothing but drift velocity. And coming to the mobility, the next one, mobility. So it is denoted by the letter mu. And what is mobility means? Generally it is expressed as mu is equal to ratio of drift velocity to the applied electric field. Okay, so it is defined as the drift velocity acquired by the free electron per unit electric field. Okay, that is E, capital E is the applied electric field. And next one is collision time. So what is collision time means? That is the average time taken by the free electron between the two successive collision. That is called as collision time. So what is collision time? It is the average time taken by the free electron between the two successive collision. Okay, it is denoted by tau c. For time, we usually we use the letter. Usually we have the letter T, and for italic T represents the relaxation time, and tau c represents the collision time. Okay, and coming to the relaxation time. So what is relaxation time means? That is the time taken by the free electron to reach its equilibrium position from its disturbed position. You got it? So it is the time taken by the free electron to reach its equilibrium position from its disturbed position in the presence of the field, in the presence of the electric field. Okay, so that is that expression for this relaxation time. Tau is equal to L by the ratio of L by Vd, where L is the distance traveled by the electrons. Okay, and the last one is mean free path. So what is mean free path? That is the distance, that is the average distance traveled between the two successive collision. What is collision time? Average time taken by the free electron between the two successive collision. And what is that is the mean free path means? That is the average distance traveled by the free electron between the two successive collision, and it is denoted by the letter lambda. So lambda is equal to tau c, collision time, product of collision time into root mean square velocity. Okay, so we discuss what are the main three theories. We started with this classical free electron theory, and what are the success and drawbacks of this classical free electron theory. It is a macroscopic theory, that is one of the main drawback. Okay, and followed by quantum free electron theory. It is a microscopic theory and it has some drawbacks. To overcome those drawbacks, we move to the last theory as the zone theory or band theory. Okay, and then followed by this we discuss so many basic definitions. So these are the definitions: drift velocity, mobility, mean free path, collision time, and relaxation time. Okay. And coming to the, because in order to derive the expression for density of energy state, we must know what is Fermi energy level and Fermi function. Okay. So Fermi function, it is denoted by f of E. So it is a probability term. Fermi function is a probability term. It is a probability of finding the particle or the electron. So f of E is equal to 1 divided by 1 plus exponential of E minus EF by kBT. That is the Fermi function. It's a probability term. What do you mean by Fermi energy level means? So at 0 Kelvin, remember, it's very important, at 0 Kelvin, the maximum level up to which the electrons can be filled. So that is the Fermi energy level. So what I told, Fermi energy level is nothing but that is at 0 Kelvin, the maximum level up to which the electrons can be filled. So what is this importance of this Fermi energy level means? It can act as a reference level to distinguish or to separate the filled and empty states. Okay, that is the Fermi energy level. So Fermi function, I told, it is a probability term. It is a probability of finding the electron in a particular energy interval or time. Okay, so that is the Fermi function and Fermi level. So in the next class, we will discuss the density of energy states. For that, you should know what is Fermi function, okay, F of E. And the entire derivation will be discussed in the next class, okay. Thank you. Hello all, good morning. So in the last class, we discussed about this Fermi energy, Fermi function, and what is Fermi level. And you know, Fermi function is it's a probability term. It doesn't give the exact number of energy state. It is a probability term. So in order to know the number of available energy states, we should go for this density of energy states. So in this session, we are going to discuss about this density of energy states and carrier concentration in metals. So before entering into the derivation part of this density of energy states, we should know the definition for density of energy states. So density of energy state is defined as the number of available energy states per unit volume in a particular energy interval. Okay. So coming to the definition of density of energy states, I said it is nothing but the number of available energy states per unit volume in a particular energy interval d. Okay. So that is the definition. And we have to obtain the expression for density of energy states. Z of E d. We have to prove that is Z of E d is equal to pi by 2 8m by h square the whole part 3 by 2 e power half t. So this is the expression for the density of energy state. And if they ask to write the carrier concentration, means you have to write that is n of E d. This is nothing but Z of E d into f of E. Okay. After getting the value of Z of E d, we have to multiply with this Fermi function. We can get the number of filled energy states, that is nothing but carrier concentration in metal. So look at the previous slide and look at the diagram. So I will draw the diagram. So the density of energy state can be obtained by the various combination of quantum numbers nx, ny, and nz. So we have to construct a sphere in a three-dimensional space and draw two spheres of radii. First one is n, another one is n plus dn. So the first one is n, another one is so the first sphere n, another one is plus dn. That is the energy of the first one is E, another one is E plus D. Okay. So we have to consider a sphere of radii n, another one is n plus dn corresponding to the energy levels E and E plus D. So we have to find the number of available energy states within this energy interval, that is this this is nothing but dE or del E, okay, within this energy interval. So in order to find this, you know what is the volume of the sphere. So volume of the sphere is nothing but 4 by 3 pi r cube. So here we assume the radius as n. So the volume of the sphere is nothing but 4 by 3 pi n cube. And similarly for the next sphere, the volume is 4 by 3 pi n plus dn the whole cube, right? So number of available energy states within the sphere of radius n is equal to, or the energy means you put it as E, that is 4 by 3 pi n cube, right? And similarly for the next sphere, n plus dn means it is nothing but 4 by 3 pi n plus dn the whole. Okay, so I'm going to multiply with 1 by 8 to this volume of the sphere. Why I am going to multiply with 1 by 8 means, see, while drawing the diagram, we put some quantum numbers nx, ny, and nz. These quantum numbers can have only positive values. So if you imagine a sphere, in this sphere, 1 by 8th or 1 octant of the sphere volume can have this positive values of quantum numbers. Okay, so directly I can write. So here we have to multiply with that is equal to 1 by 8 into this volume of the sphere. I said why I multiply with this 1 by 8 means, since the quantum numbers can have only positive values. So in the sphere volume, I said 1 octar, 1 by 8th portion can have this portion of the sphere can have this positive values. So I multiply with this 1 by 8, let it be equation number 1. Okay. And similarly, number of, we have to write the same sentence, available energy states within the sphere of radius n plus dn is equal to, again write the same, 1 by 8 into 4 by 3 pi n plus dn the whole cube. Okay, therefore let it be equation number 2. Therefore the number of energy states within the energy interval E and E plus dE, or n and n plus dn. You can write any one, either radius or could take this energy interval, that is equal to, subtract equation 2 minus 1. Okay, so take the common terms, 1 by 8, 4 by 3 pi, so n plus dn the whole cube minus n cube, right? So that is equal to, you cancel this, so pi by 6 into, expand this n plus dn, that is in the format of a plus b the whole cube. So expand this, a cube plus b cube plus 3a square b plus 3a b square minus this n cube. Understand? Okay. So neglecting the higher powers of dn, because that energy dn is a very small thickness, and if we go for the higher powers, it will be negligible. Okay, so neglecting the higher powers of dn, so we can get, so cancel this term, and this dn square get cancelled, this n cube plus n cube minus n cube get cancelled, so we have only 3n square dn, pi by 6 into 3n square dn. So let it be z of e, that is z of e, that is number of energy states within the energy interval, that is nothing but z of e d is equal to pi by 6 3n square dn. Okay, so again once again cancel this, so it becomes pi by 2 n square dn, or it can be written as pi by 2 n dot n dn. For our simplification, we write like this, n dot n dn. Okay, so this is nothing but number of available energy states within the energy interval. Z of E d is equal to pi by 2 n dot n d. So let it be equation number 3 or 4. Okay. So this is first part of this derivation. And you know that in the last semester you studied this application of Schrödinger's equation in one-dimensional box. We got some eigenvalues and eigenfunction. Okay, and you know that the energy of an electron, that is the energy, that is eigenvalue, the energy of an electron in a potential well of length L is given as, that is energy is equal to n squared h squared by 8 m L squared. Okay, that is equation number 5. So you know this expression, that is energy eigenvalue or energy is equal to n squared h squared by 8 m L squared. So we are going to replace in the fourth equation, we are going to replace that n and n dn. Okay, so from this expression find out this n square, make some rearrangements. So n square is nothing but 8 m L square by h square into this e. Okay, so this is nothing but n square. So this is n square means and you know what is n? N is nothing but square root of that value, 8m L square e by h square the whole power 1 by 2. Okay, and differentiate this n square. So differentiating this n squared with respect to n, we have, so after differentiating we can get, that is 2n. 2n dn is equal to 8m L square by h square into differentiating e means d, or we need therefore n dn is equal to 8m L square by 2 h square into d. So let it be equation number 6, and this is a 7. Now we are going to substitute equation 6 and 7 in equation number 4. So instead of this n value, I'm going to substitute equation 6, and instead of this n dn, we have this expression equation number 7. Okay. therefore z of E d is equal to pi by 2. What is n? N is nothing but 8m L squared by h squared into E the whole power half. This is n. And n dn is nothing but 8m L squared by 2h squared into d. Okay. So this is equation number 8. So I substituted the value of n and n dn. Okay. So unsimplify this now. So you could see here 8m L square by h square power half, and then this is 8m L square by 2h square. So bring this to outside. So it becomes pi by 4 and 8m L square by h square the whole power half, and here is 8m L squared by h square the whole power 1, and keep this e power half into d. And look at the powers. This is power half and this is power 1. So we can write it as pi by 4 8m L square by h square the whole power 3 by 2, right? E power half d. Okay. So this is nothing but z of E d. So according to Pauli's principle, maximum of 2 electrons can occupy in each energy state. You know that. Okay. So multiply by 2. This is equation number 9. So if you multiply this 2, so z of E dE becomes 2 into pi by 4 into 8m by h square into L square the whole power 3 by 2 into e power half d. So it becomes, so that is z of E d is equal to pi by 2 8m by h square L square the whole power 3 by 2 e power half d. And look at this, the term that is L square the whole power 3 by 2. So you can cancel this 2. So it becomes L cube. L cube is nothing but 1 by definition, because in definition I said that is nothing but the number of available energy state per unit volume in a particular energy interval. Okay. So this is nothing but z of E d is equal to pi by 2 8m by h square the whole power 3 by 2 e power half dE. So this is nothing but the expression for this density of energy state. Okay. And to obtain the carrier concentration,
we assume that N of ED is the number of field energy state. N of ED is the number of field energy state, and normally all the energy states will not be filled, and in order to the number of field energy state we have to multiply with this Fermi function to this number of available energy state. So Z of EDE into F of E. So that is 5 by 2, 8 term by H square, the whole power 3 by 2, e power half dE into F of. So this is nothing but N of E d. So that will be equation number 8, 9 or this is 9. That will be equation number 10. Okay. So this is the expression for carrier concentration in metals.
இப்போதாம்மா ரெக்கார்ட் ஆகுது.
இந்த முன்னாடி தான் எப்படி எழுதுங்க? Hi, welcome you all. for this session. And in today's class, we are going to discuss about this CNOT gate. And you know what is a CNOT gate? It is nothing but a controlled NOT gate. CNOT gate is a controlled NOT gate. And also it is called as a reversible XOR gate. And we can call it as a 2-qubit quantum gate. CNOT gate, I said it is nothing but controlled NOT gate or reversible XOR gate or 2-qubit quantum gate. Okay, so it is nothing but a quantum logic gate that plays a vital role in the designing of quantum computers. And it has, this is the only gate having 2 inputs and 2 outputs. It has 2-qubit operation, out of which the first one is called as controlled qubit and the second one is target qubit. And coming to the logical representation of this CNOT gate, and I will draw the symbol and logical representation. Coming to the symbol and logical representation. And you know, you might have studied the basic gates, logic gates. And I said it is a reversible XOR gate, and there exist 2 horizontal lines. This another one. And this one is controlled qubit. Controlled qubit, and this is target qubit. So let it be, this is A and this is B, and the vertical line joins this controlled and then quantum qubit, and this is the output. So you can write it as this is X or Y. Okay, so the control qubit is nothing but X and the target qubit is the Y. Okay, and we have to connect. Okay, so this is the symbol. And next we see the logical representation. So coming to the logical representation, so this is nothing but a XOR gate. Okay. And there are, I said this is the only gate having two input and then two outputs. Sorry. So let it be, this is A, and this is B. This is A and this is B, and this is nothing but X. Okay. So this is a XOR gate. So this is the target and this one is the control. Okay, so this is the output Y. This is one output and this is our another output A XOR B. That is equal to AB bar plus A bar B. Okay. So this is the logical representation, and if the output Y that depends on the control qubit A and target qubit B. Okay. So here if the source or control A is equal to 0, listen carefully, if the source or the control A is equal to 0, then the output will be, that is the output Y is equal to the value of B, that is nothing but target. Okay. At the same time, if that is the A value is equal to, that is the source or control qubit is equal to 1, then the output Y will be inverse of this B value. That is, it is nothing but inverse of this B. So inverse of this target. So while drawing this truth table, you could understand this concept. So coming to the truth table, so we have two inputs, right? And I said this is the only gate having two inputs and then two outputs. So I draw this truth table. This is input, and we have two inputs, that is X or Y or A or B, whatever it may be. So this is A and B, and one is controlled, another one is target. One is control, another one is target. So this is control and this is target. Okay. So this is input and output. that is output X and Y. And write the basic states 0, 0, 0, 1, 1, 0, 1, 1. So look at this logical representation. So in the logical representation, that is, you could see in the diagram, that is the input is directly connected to the X. So whatever the values assigned in the control qubit, that will be reflected in the output for X. So simply you can write it as this is 0, 0, 1, 1. Okay. So this is 0, 0, 1, 1. That's very simple. And I said wherever we get 1, if it is 0 means you can write the value as it is. Okay. So this is nothing but 0. So 0 state means you can simply write it as 0, and here it is a 0. Control qubit is 0 means it won't affect this target qubit. So simply write it as 0 means 0 and 1 here means 1. Okay. And if it is in one state, that is the control qubit is in one state, then it will flip this target qubit and the value becomes inverse. So if it is 0 means it becomes 1, and if it is 1 means it becomes 0. Okay. So now you could understand, that is why I wrote this. If the control qubit A is equal to 0, then the output Y will be as it is target qubit B. And if the control qubit A is equal to 1 state means I said that is the output Y will be the inverse of this target qubit. Okay. So this is the truth table. And coming to this, that is the matrix of this CNOT gate. And so it's very simple. And write the matrix. I said it has a 4 state, that is 0, 0, 0, 1, 1, 0 and 1, 1 state. It has 4 state. It is the matrix is 4 state. And first state for 0, 0, that is equal to, in qubit we can write as 0 means 1, 0. This is classical. And this is in quantum, we can write it as 1, 0. And then a 0 means once again 1, 0. So if we go for multiplication, so 1, 0, 0, 0. So 1, 0, 0, 0. Okay. That is for 0, 0 state. And coming to the next state, 0, 1. So if it is in 0 means, in classical state it is in 0 means it is nothing but 1, 0. And if it is in one state means we can write it as in quantum state, it is nothing but 0, 1. Okay. This and all you know. So after multiplication, we can get 1 into 0, 0, 1 into 1, 0, 1, and 0 into 0, once again 0, and 0 into 1, once again 0. So this is for the second. And similarly, coming to the third, that is 0, 0, 0, 1, and then 1, 0. For 1, 0 state, we can write for 1 means 0, 1, and for 0 means 1 0. So go for multiplication. The similar procedure you have to apply for all the for each steps. Okay. So 0 into 1, it is nothing but 0, and then 0 into 0, 0, 1 into 1, it becomes 1, and 1 into 0, it becomes 0. Okay. And coming to the last one, that is 1 1 state, that is equal to 1 means 0 1, and similarly 0 1. So that is equal to 0, and again 0, again 0, and then last one is 1. Now combine all these things and we can get the output of the C naught gate. So therefore the output of C naught is that is the matrix is that is equal to, you can combine all these four states, that is 1 0 0 0 0 1 0 0 0 0 1 0, and then 0 0 0 1. Okay, so this is the matrix form of this C naught gate. And coming to the uses of this C naught, and I said, sorry, it is used to generate entanglement and also superposition. And by using this, we can construct all the gates and we can do all the mathematical operations. Okay. So in general, this it is represented as, that is A B. This is a representation of this C naught gate, and all we discussed, this A is nothing but control qubit, and B is the target qubit, and the control qubit is operated on the target qubit. If the control qubit is 0, definitely it won't affect this target qubit. If it is 1, then it flips the target qubit. Okay. So this is all about this C naught gate. Okay. And the in next class we'll discuss about this another one new topic. Okay. Thank you all.